Hello, my name is Saujanya Verma, and this is my presentation on cooling of electronics for the class heat treatment.
Here are all the topics that we will go through today: the introduction, cooling methods, the thermal environment, electronics cooling in different applications, conduction cooling, conduction in chip carriers, conduction in PCBs, air cooling, natural and forced convection, fan selection, and some general guidelines.
Let's go through the introduction. Recent development in semiconductor and other mini and microscale electronic technologies and continued miniaturization have led to very high increase in power density for high performance chips. Although impressive progress has been made during the past decades, there remain serious technical challenges in thermal management and control of electronics devices or microprocessors. The two main challenges are adequate removal of ever increasing heat flux and highly non uniform power dissipation. Conventional cooling approaches are increasingly falling apart to deal with the high cooling demand and thermal management challenges of emerging electronic devices. Thus, high performance chips or devices need innovative techniques, mechanisms, and coolants with high heat transfer capability to enhance the heat removal rate in order to maintain their normal operating temperature. Unless they are cooled properly, their normal performance and longevity can deteriorate faster than expected. In addition, the failure rate of electronic equipment increases with increasing operating temperature. Let us go through some of the cooling methods. There are a number of cooling methods widely used in electronic industries. Based on heat transfer effectiveness, the existing cooling modes can be classified into four general categories, which are natural convection, forced convection air cooling, forced convection liquid cooling, and liquid evaporation. Based on the approximate range of heat flux removal rate of these methods, it is known that liquid evaporation is the best technique, followed by the forced convection of liquids and then air. However, forced air convection, which is widely used in cooling electronics such as CPU of computing devices, has very low heat removal rate, though higher than radiation and natural convection. Besides heat removal mode, cooling fluids also play a major role in overall cooling performance. Now let us talk about the thermal environment. An important consideration in the selection of a cooling technique is the environment in which the electronic equipment is to operate. Simple ventilation holes on the case may be all we need for the cooling of low power density electronics such as a TV or a VCR in a room, and a fan may be adequate for the safe operation of a home computer. But the thermal control of the electronics of an aircraft will challenge thermal designers, since the environmental conditions in this case will swing from one extreme to another in a matter of minutes. The expected duration of operation in a hostile environment is also an important consideration in the design process. The thermal environment in marine applications is relatively stable, since the ultimate heat sink in this case is water with a temperature range of 0 degrees Celsius to 30 degrees Celsius. For ground applications, however, the ultimate heat sink is the atmospheric air, whose temperature varies from minus 50 degrees Celsius at polar regions to plus 50 degrees Celsius in desert climates, and whose pressure ranges from about 70 kilopascal at 3000 meter elevation to 107 kilopascals at 500 meters below the sea level. In airborne applications, the thermal environment can change from 1 atm and 35 degrees Celsius on the ground to 19 kilopascal or zero point 0.2 atm and 60 degrees Celsius at a typical cruising altitude of 12,000 meters in minutes. At supersonic velocities, the surface temperature of some part of the aircraft may rise to 200 degrees Celsius above the environment temperature. Electronic devices are rarely exposed to uncontrolled environmental conditions directly because of the wide variations in the environmental variables. Instead, a conditioned fluid such as air, water, or a dielectric fluid is used to serve as a local heat sink and as an intermediary between the electronic equipment and the environment. Just like the air conditioned air in a building providing thermal comfort to the human body. Conditioned air is the preferred cooling medium since it is benign, readily available, and not prone to leakage, but its use is limited to equipment with low power densities because of the low thermal conductivity of air. The thermal design of electronic equipment in military applications must comply with strict military standards in order to satisfy the utmost reliability requirements. Electronics cooling in different applications. The cooling techniques used in the cooling of electronic equipment may vary widely depending on the particular application. For example, the electronics of short-range missiles do not need any cooling because of their short cruising times. The missiles reach their destinations before the electronics reach unsafe temperatures. Long-range missiles, such as cruise missiles, however, may have a flight time of several hours, therefore, they must utilize some form of cooling mechanism. The first thing that comes to mind is to use forced convection with the air that rams the missile by utilizing its large dynamic pressure. However, the dynamic temperature of air, which is the rise in the temperature of air as a result of the ramming effect, may be more than 50 degrees Celsius at speeds close to the speed of sound. For example, at a speed of 320 meters per second, the dynamic temperature of air can be calculated as T dynamic is equal to V square by 2 Cp, where Cp is the heat capacity of air. This equation gives us 51 degrees Celsius. Therefore, the temperature of air at a velocity of 320 meters per second and a temperature of 30 degrees will rise to 81 degrees as a result of conversion of kinetic energy to internal energy. Air at such high temperatures is not suitable for use as a cooling medium. Instead, cruise missiles are often cooled by taking advantage of the cooling capacity of the large quantities of liquid fuel they carry. The electronics in this case are cooled by passing the fuel through the cold plate of the electronic enclosure as it flows toward the combustion chamber. Electronic equipment in space vehicles is usually cooled by a liquid circulated through the components, where heat is picked up and then through a space radiator, where the waste heat is radiated into deep space at about 0 Kelvin. We should note that radiation is the only heat transfer mechanism for rejecting heat to the vacuum environment of space, and radiation exchange depends strongly on surface properties. Desirable radiation properties on surfaces can be obtained by special coatings and surface treatments. When electronics in sealed boxes are cooled by liquid flowing through the outer surface of the electronics box, it is important to run a fan in the box to circulate the air, since there are no natural convection currents in space because of the absence of a gravity field. Electronic equipment in ships and submarines is usually housed in rugged cabinets to protect it from vibrations and shock during a stormy weather. Because of easy access to water, water-cooled heat exchangers are commonly used to cool shipboard electronics. This is usually done by cooling air in a closed or open loop air to water heat exchanger and forcing the cool air to the electronic cabinet by a fan. When forced air cooling is used, it is important to establish a flow path of air such that no trapped hot air pockets will be formed in the cabinets. Communication systems located at remote locations offer challenges to the thermal designers because of extreme conditions under which they operate. These electronic systems operate for long periods of time under adverse conditions such as rain, snow, high winds, solar radiation, high altitude, high humidity, and extremely high or low temperatures. Large communication systems are housed in specifically built shelters. Sometimes it is necessary to air condition these shelters to safely dissipate the large quantities of heat dissipated by the electronics of the communication systems. The manufacturers of electronic devices usually specify the rate of heat dissipation and the maximum allowable component temperature for reliable operation. These two numbers help us determine the cooling techniques that are suitable for the device under consideration. Conduction cooling. Heat is generated in electronic components whenever electric current flows through them. The generated heat causes the temperature of the components to rise, and the resulting temperature difference drives the heat away from the components through a path of least thermal resistance. The temperature of the components stabilizes when the heat dissipated equals the heat generated. In order to minimize the temperature rise of the components, effective heat transfer paths must be established between the components and the ultimate heat sink, which is usually the atmospheric air. Conduction cooling is based on the diffusion of heat through solid, liquid, or gas as a result of molecular interactions in the absence of any bulk fluid motion. Steady one-dimensional heat conduction through a plane medium of thickness L, heat transfer surface area A, and thermal conductivity K is given by Q is equal to Ka delta T by L or delta T by R, where R is equal to L by Ka. Here R is the thermal resistance of the medium and T is the temperature difference across the medium. This is analogous to the electric current being equal to the potential difference divided by the electrical resistance. Conduction in chip carriers. The conduction analysis of an electronic device starts with the circuitry or junction of a chip, which is the site of heat generation. The heat generated at the junction spreads throughout the chip and is conducted across the thickness of the chip. The spread of heat from the junction to the body of the chip is three-dimensional in nature but can be approximated as one-dimensional by adding a constriction thermal resistance to the thermal resistance network. For a small heat generation area of diameter d on a considerably larger body, the constriction resistance is given by R constriction is equal to 1 upon square root of pi dk, where k is the thermal conductivity of the larger body. The chip is attached to the lead frame with a highly conductive bonding material that provides a low resistance path for heat flow from the chip to the lead frame. There is no metal connection between the lead frame and the leads since this would short circuit the entire chip. Therefore, heat flow from the lead frame to the lead is through the dielectric case material such as plastic or ceramic. Heat is then transported outside the electronic device through the leads. When solving a heat transfer problem, it is often necessary to make some simplifying assumptions regarding the primary heat flow path and the magnitudes of heat transfer in other directions. In the chip carrier discussed previously, the heat transfer through the top is disregarded since it is very small because of the large thermal resistance of the stagnant air space between the chip and the lid. Heat transfer from the base of the electronic device is also considered to be negligible because of the low thermal conductivity of the case material and the lack of effective convection on the base surface. Conduction in printed circuit boards. Heat generating electronic devices are commonly mounted on thin rectangular boards, usually 10 cm into 15 cm in size, made of electrically insulating materials such as glass epoxy laminates, which are also poor conductors of heat. The resulting printed circuit boards are usually cooled by blowing air or passing a dielectric liquid through them. In such cases, the components on the PCBs are cooled directly, and we are not concerned about the heat conduction along the PCBs. But in some critical applications, such as those encountered in the military, the PCBs are contained in sealed enclosures, and the boards provide the only effective heat path between the components and the heatsink attached to the sealed enclosure. In such cases, heat transfer from the side faces of the PCBs is negligible, and the heat generated in the components must be conducted along the PCB towards its edges, which are clamped to cold plates for removing the heat externally. Heat transfer along a PCB is complicated in nature because of the multi-dimensional effects and non-uniform heat generation on the surfaces. We can still obtain sufficiently accurate results by using the thermal resistance network in one or more dimensions. Copper or aluminum cladding, heat frames, or cores are commonly used to enhance heat conduction along the PCBs. When analyzing heat conduction along a PCB with copper or aluminum cladding on one or both sides, often the question arises whether heat transfer along the epoxy laminate can be ignored relative to that along the copper layer, since the thermal conductivity of copper is about 1500 times that of epoxy. The answer depends on the relative cross-sectional areas of each layer, since heat conduction is proportional to the cross-sectional area as well as the thermal conductivity. Now let us take an example of a PCB, and here you can see the diagram of that PCB. The Q indicates the heat transferring from this side to the opposite side. The upper layer is epoxy and the lower layer is copper. T epoxy is the thickness of the epoxy layer and T copper is the thickness of the copper layer, and the thickness of the whole PCB is equal to T epoxy plus T copper. Consider a copper-cladded PCB of width W and length L, across which the temperature difference is delta T as shown in the earlier slide. Assuming heat conduction is along the length L only and heat conduction in other dimensions is negligible, the rate of heat conduction along this PCB is the sum of heat conduction along the epoxy board and the copper layer and can be expressed as Q of PCB is equal to Q of epoxy plus Q of copper. We can solve the equation further as Ka delta T by L of epoxy plus Ka delta T by L of copper. Upon further solving the equation, it comes out to be Kt of epoxy plus Kt of copper multiplied by W delta T by L. Here T denotes the thickness. Therefore, the relative magnitudes of heat conduction along the two layers depend on the relative magnitudes of the thermal conductivity thickness product Kt of the layer. Therefore, if the Kt product of copper is 100 times that of epoxy, then the neglecting heat conduction along the epoxy board will involve an error of just 1%, which is negligible. We can also define an effective thermal conductivity for metal cladded PCBs as K effective is equal to Kt of epoxy plus Kt of copper divided by thickness of epoxy plus thickness of copper watt per meter per degree Celsius. So the rate of heat conduction along the PCB can be expressed as Q PCB is equal to K effective into thickness of epoxy plus thickness of copper into width delta T by L is equal to K effective into area of PCB delta T by L, where A PCB is equal to W thickness of epoxy plus thickness of copper is the area normal to the direction of the heat transfer. When there are holes or discontinuities along the copper cladding, the above analysis needs to be modified to account for the effect. In applications where direct cooling of circuit boards by passing air or a dielectric liquid over the electronic components is not allowed and the junction temperatures are to be maintained relatively low to meet strict safety requirements, a thick heat frame is used instead of a thin layer of copper cladding. This is especially the case for multi-layer PCBs that are packed with high power output chips. Heat generated in the chips is conducted through the circuit board, through the epoxy adhesive to the center of the heat frame, along the heat frame, and to a heat skin or cold plate, where heat is externally removed. The heat frame provides a low resistance path for the flow of heat from the circuit board to the heatsink. The thicker the heat frame, the lower the thermal resistance, and thus the smaller the temperature difference between the center and the ends of the heat frame. When a heat frame is used, heat conduction in the epoxy layer of the PCB is through its thickness instead of along its length. The epoxy layer in this case offers a much smaller resistance to heat flow because of the short distance involved. Air cooling, natural convection, and radiation. Low power electronic systems are conveniently cooled by natural convection and radiation. Natural convection cooling is very desirable since it does not involve any fans that may break down. Natural convection is based on the fluid motion caused by the density differences in a fluid due to a temperature difference. A fluid expands when heated and becomes less dense. In a gravitational field, this lighter fluid rises and initiates a motion in the fluid called natural convection currents. Natural convection cooling is most effective when the path of the fluid is relatively free of obstacles which tend to slow down the fluid, and is least effective when the fluid has to pass through narrow flow passages and over many obstacles. The magnitude of the natural convection heat transfer between a surface and a fluid is directly related to the flow rate of the fluid. The higher the flow rate, the higher the heat transfer rate. In natural convection, no blowers are used and therefore the flow rate cannot be controlled externally. The flow rate in this case is established by the dynamic balance of buoyancy and friction. The larger the temperature difference between the fluid adjacent to a hot surface and the fluid away from it, the larger the buoyancy force and the stronger the natural convection currents, and thus the higher the heat transfer rate. Electronic components or PCBs placed in enclosures such as a TV or VCR are cooled by natural convection by providing a sufficient number of vents on the case to enable the cool air to enter and the heated air to leave the case freely. From the heat transfer point of view, the vent should be as large as possible to minimize the flow resistance and should be located at the bottom of the case for air entering and at the top for air leaving. But equipment and human safety requirements dictate that the vents should be quite narrow to discourage unintended entry into the box.
The heat transfer from a surface at temperature Ts to a fluid at temperature T fluid by convection is expressed as Q is equal to HA delta T is equal to HA Ts minus T fluid, where H convection is the convection heat transfer coefficient and AS is the heat transfer surface area. The value of H convection depends on the geometry of the surface and the type of fluid flow, among other things. Natural convection currents start out as laminar, smooth and orderly, and turn turbulent when the dimension of the body and the temperature difference between the hot surface and the fluid are large. For air, the flow remains laminar when the temperature differences involved are less than 100 degrees Celsius and the characteristic length of the body is less than 0.5 meter, which is almost always the case in electronic equipment. Therefore, the flow in the analysis of the electronic equipment can be assumed to be laminar. The natural convection heat transfer coefficient for laminar flow of air at atmospheric pressure is given by a simplified relation of the form H convection is equal to K delta T by L raised to the power of 0.25, where delta T is equal to Ts minus T fluid, which is the temperature difference between the surface and the fluid. L is the characteristic length, the length of the body along the heat flow path, and K is a constant whose value depends on the geometry and orientation of the body.
When hot surfaces are surrounded by cooler surfaces, such as the walls and ceilings of a room or just the sky, the surfaces are also cooled by radiation. The magnitude of radiation heat transfer in general is comparable to the magnitude of natural convection heat transfer. This is especially the case for surfaces whose emissivity is close to unity, such as plastics and painted surfaces, regardless of the color. Radiation heat transfer is negligible for polished metals because of their very low emissivity and for bodies surrounded by surfaces at about the same temperature. Radiation heat transfer between a surface at temperature Ts completely surrounded by a much larger surface at temperature T surrounding can be expressed as Q is equal to Ea sigma T surface whole to the power 4 minus T surrounding to the power 4, where E is the emissivity of the surface, as is the heat of the transverse surface area and is the Stefan Boltzmann constant. Arrays of low power PCBs are often cooled by natural convection by mounting them within a chassis with adequate openings at the top and at the bottom to facilitate airflow. The air between the PCBs rises when the heated by the electronic components and is replaced by the cooler air entering from below. This initiates the natural convection flow through the parallel flow passages formed by the PCBs. The PCBs must be placed vertically to take advantage of natural convection currents and to minimize trapped air pockets. Placing the PCBs too far from each other wastes valuable cabinet space, and placing them too close tends to choke the flow because of the increased resistance. Therefore, there should be an optimum spacing between the PCBs. In the heat transfer analysis of PCBs, radiation heat transfer is disregarded since the view of the components is largely blocked by other heat generating components. As a result, hot components face other hot components instead of a cooler surface. The exceptions are the two PCBs at the end of the chassis that view the cooler side surfaces. Therefore, it is wise to mount any high power components on the PCBs facing the walls of the chassis to take advantage of the additional cooling provided by radiation. Heat transfer from PCBs can be analyzed by treating them as rectangular plates with uniformly distributed heat sources on one side and insulated on the other side. Since heat transfer from back surfaces of the PCBs is usually small, it should be remembered that natural convection currents only occur in gravitational fields. Therefore, there can be no heat transfer in space by natural convection. This will also be the case when the air passageways are blocked and hot air cannot rise. In such cases, there will be no motion and no heat transfer through the air will be by convection. The heat transfer from hot surfaces by natural convection and radiation can be further enhanced by attaching fins to the surfaces. Air cooling, forced convection. The convection heat transfer between a solid surface and a fluid is proportional to the velocity of the fluid. The higher the velocity, the larger the flow rate and the higher the heat transfer rate. The fluid velocities associated with natural convection currents are naturally low, and thus natural convection cooling is limited to low power electronic systems. When natural convection cooling is not adequate, we simply add a fan and blow air through the enclosure that houses the electric components. In other words, we resort to forced convection in order to enhance the velocity and thus the flow rate of the fluid as well as the heat transfer. By doing so, we can increase the heat transfer coefficient by a factor of up to about 10 depending upon the size of the fan. This means that we can remove heat at much higher rates for a specified temperature difference between the components and the air, or we can reduce the surface temperature of the components considerably for a specified power dissipation. The radiation heat transfer in forced convection cooled electronic systems is usually disregarded for two reasons. First, forced convection heat transfer is usually much larger than that due to radiation, and the consideration of radiation causes no significant changes in the results. Second, the electronic components and circuit boards in convection cooled systems are mounted so close to each other that a component is almost entirely surrounded by other components at about the same high temperature. That is, the components have hardly any direct view of a cooler surface. This results in little or no radiation heat transfer from the components. The components near the edges of circuit boards with a large view of a cooler surface may benefit from somewhat of the additional cooling by radiation, and it is a good design practice to reserve those spots for high power components to have a thermally balanced system. When heat transfer from the outer surface of the enclosure of the electronic equipment is negligible, the amount of heat absorbed by the air becomes equal to the amount of heat rejected or power dissipated by the electronic components in the enclosure and can be expressed as Q is equal to mc delta T, where Q is the rate of heat transfer to the air, Cp is the specific heat of air, T in and T out are the average temperatures of air at the inlet and exit of the enclosure, respectively, and m is the mass flow rate of air. Note that for a specified mass flow rate and power dissipation, the temperature rise of air T out T in remains constant as it flows through the enclosure. Therefore, the higher the inlet temperature of air, the higher the exit temperature, and thus the higher the surface temperature of the components. Fan selection. A fan at a fixed speed or fixed RPM will deliver a fixed volume of air regardless of the altitude and pressure. But the mass flow rate of the air will be less at high altitude as a result of lower density of air. For example, the atmospheric pressure of air drops by more than 50% at an altitude of 6,000 meters from its value at sea level. This means that the fan will deliver half as much air mass at this altitude at the same RPM and temperature, and thus the temperature rise of air cooling will double. This may create serious reliability problems and catastrophic failures of electronic equipment if proper precautions are not taken. Variable speed fans that automatically increase speed when the air density decreases are available to avoid such problems. Expensive electronic systems are usually equipped with thermal cutoff switches to prevent overheating due to inadequate airflow rate or the failure of the cooling fan.
Fans draw in not only cooling air but also all kinds of contaminants that are present in the air, such as lint, dust, moisture, and even oil. If unattended, These contaminants can pile up on the components and plug up narrow passageways, causing overheating. It should be remembered that the dust that settles on the electronic components acts as an insulation layer that makes it very difficult for the heat generated in the component to escape. To minimize the contamination problem, air filters are commonly used. It is good practice to use the largest air filter practical to minimize the pressure drop of air and to maximize the dust capacity.
Here are some general guidelines for forced air cooling of electronic systems. Before deciding on forced air cooling, check to see if natural convection cooling is adequate. If it is, which may be the case for low power systems, incorporate it and avoid all the problems associated with fans such as cost, power consumption, noise, complexity, maintenance, and possible failure. Select a fan that is neither too small nor too large. An undersized fan may cause the electronic system to overheat and fail. An oversized fan will definitely provide adequate cooling, but it will needlessly be larger and more expensive and will consume more power. If the temperature rise of air due to the power consumed by the motor of the fan is acceptable, mount the fan at the inlet of the box to pressurize the box and filter the air to keep the dirt and dust out. Position and size the air exit vents so that there is adequate airflow throughout the entire box. More air can be directed to a certain area by enlarging the size of the vent at that area. The total exit areas should be at least as large as the inlet flow area to avoid choking of the airflow, which may result in reduced airflow rate. Place the most critical electronic components near the entrance where the air is coolest. Place the non-critical components that consume a lot of power near the exit. Arrange the circuit boards and the electronic components in the box such that the resistance of the box to airflow is minimized and thus the flow rate of air through the box is maximized for the same fan speed. Make sure that no hot air pockets are formed during operation. Consider the effect of altitude in high altitude applications. Try to avoid any flow sections that increase the flow resistance of the systems, such as unnecessary corners, sharp turns, sudden expansions and contractions, and very high velocities greater than 7 meters per second. Since the flow resistance is nearly proportional to the flow rate, also avoid very low velocities since these result in a poor heat transfer performance and allow the dirt and the dust in the air to settle on the components. Arrange the system such that natural convection helps forced convection instead of hurting it. For example, mount the PCBs vertically and blow the air from the bottom towards the top instead of the other way around. When the design calls for the use of two or more fans, a decision needs to be made about mounting the fans in parallel or in series. Fans mounted in series will boost the pressure head available and are best suited for systems with a high flow resistance. Fans connected in parallel will increase the flow rate of air and are best suited for systems with small flow resistance.
Thank you for your time.